Thanks for tuning in again. This is Daniel Kovac with another tutorial on R. If you recall, before we covered installing this language on the Windows 7 operating system. Now we will go through some of the very basics of this computing language. If you are an experienced R user, you can feel free to skip this or otherwise treat it as a refresher. R is a language that is gaining popularity in the math and science communities. It's great for prototyping, data mining, modeling and simulation, graphing, and much, much more. So let's get started. First, click on the Cygwin icon, then type R to start the R interpreter. If you recall, the very last thing we did in the last tutorial was to get the R interpreter to print the words "Hello World" to the screen. Let's move on and introduce some new features. Since R is a math and science platform, one would expect that it could deal with basic addition and subtraction of integers, and we see that it can. We can also do exponentiation and assigning of variables. There are two different ways to do this. The first is with the arrow operator, and the second is with the equal sign. If we assign a number to x and press X, then we get the desired result. We can also reference x using the print function. Let's try another way. Let's set x equal to 5. Now we see that we got the same result. There is a difference between these operators, and it has to do with the concept of scope, which is a bit beyond the scope of our tutorial. We can concatenate objects using the C function, as shown here. This function is very useful, and we'll be using it a lot in this tutorial. The concatenate function is very versatile, and we don't just have to use it with numbers. We can also use it with strings or Boolean values, or even more complicated structures that we'll deal with later. Let's try using the concatenate function with strings. In R, you can create a string by encapsulating a series of characters in double or single quotes. Now let's try concatenating another data type. This time we'll use the Boolean values true or false. These are represented by spelling out the words true or false in all capital letters. Let's call the print function one more time just to make sure that we get what we expect. And lo and behold, we do. There's another way we could deal with Boolean values, and that is simply by abbreviating true and false to T and F respectively. This convention comes in handy when we want to avoid verbosity. But we still have not even really scratched the surface of what we can do with the concatenate function. Let's go ahead and specify a range of values. To specify a range of integers, we'll type the first one and the last one delimited by a colon. What this will do is expand out all the integers in between. We can use these ranges as indices to select values from the array X that we just created. Notice that the indices are enclosed by square brackets. If we want to select the last element, we can use the length function. Let's talk about how to deal with matrices in R. Let's clean up our work from before. We can press Ctrl L, and this will clear the interpreter to give us a nice clean working space. Let's create a 3x3 square matrix. This is accomplished by calling the matrix function and using the concatenate operator to specify the values that we want. Next, we can specify the number of rows, followed by the number of columns. If we get lazy and we don't feel like typing out the number of rows and the number of columns every single time, we need only specify one. R is smart enough to figure it out. There's a great deal of other functionality with R and matrices, and we'll only cover a very small portion of it here. Another neat thing R can do with matrices is provide row names and column names. There are many different ways to do this, and we'll only show one. What we're going to do is create an object which is a concatenation of 3 different strings because we have 3 different rows. Let's do the same thing for the column names. We'll create an object consisting of 3 different strings. Again, this is because we have 3 different columns. Now let's create a matrix with the column names and row names that we just specified. We can call the matrix function exactly as we did before by pressing the up arrow until we see it. This time we'll use the dimNames keyword and set that equal to a list consisting of the row names followed by the column names. When we print the matrix we just created, this time we'll see the row names and the column names that we specified earlier. Let's learn how to select values from our matrix. Like the previous section, we'll use the square brackets to do this, but notice that we have two values, the row and the column. To select the row number, simply enter the number of the row and a comma with nothing after it and close the bracket. If we don't want the entire row, then specify the number of the column we'd like to intersect it with after the comma. We can select an entire column by leaving a blank space where our row number was and then specifying the number of the column that we want. We can select multiple rows by using the handy concatenate function. Simply specify the rows you'd like to select. You can also specify a range of rows. This is often called array or matrix slicing. To get a feel for these different tactics, I highly recommend just playing with this yourself. Play with different combinations of all the methods that we've just talked about. Next, let's talk about the different matrix operations we can do in R. Let's create a secondary matrix for us to play with. Notice that the number of values that we specify in the matrix and the dimensionality that we want must agree. R will give us an error otherwise. Let's try again. Go ahead and change that 14 to a 16, and we see that everything works perfectly. Since our first matrix was a 3 by 3 matrix, let's go ahead and create another 3 by 3 matrix. With these new matrices, we can take a look at some of the built-in functionality that R has as far as matrix operations. Let's try matrix multiplication first. Let's use the star operator. If you're paying attention, you'll see that this is not actually the result you'd expect from conventional matrix multiplication. This is actually component-wise multiplication. For conventional matrix multiplication, we use the overloaded star operator. We simply surround our star operator by percent signs. Again, the dimensionality must agree. If it doesn't, then R will throw an error. As one would expect, we could also do basic addition and subtraction. Again, don't forget to keep in mind the dimensionality of the matrices. There's one more operation I left out, and that is component-wise division. And finally, we could take the matrix transpose by calling the function T. One of the most important and widely used features in R is the data frame. This structure provides an excellent way that you can organize and study your data under the R framework. To start, let's convert one of the matrices that we defined before into a data frame using the asDataFrame method. Notice that the row names and the column names are preserved. We can reference a column by its name using the $sign operator. Notice that since there's a space in our column names, we need to surround them by quotes. We can index into each of the columns by using the square brackets as we did with arrays and matrices. If we like, we can index data frames just like we did with matrices, and data slicing still applies. Let's create a data frame from scratch. We'll create each column separately and then bind them all together later. We create a data frame by calling the data.frame function and then specifying the columns that we want. Notice in the output that the variable names correspond to the column names in our data frame. Just like we did before, we can reference individual columns using the $ operator. Just like with matrices, there's all sorts of stuff we can do with data frames. Let's start by appending rows and columns to our data frame. The rbind function lets us append, or bind, a new row to our data frame. But this will not actually change the data frame itself. If we want our changes to stick, we need to use the assignment operator. Let's try binding a column to our data frame. This time we call the cbind function. Since we did not specify a column name, the default one that R chooses for us is rather ugly. We can correct this by creating a variable z within the bind function. Again, notice that the bind function does not actually change our data frame df. To get these changes to stick, we need to use the assignment operator. Using the assignment operator, the data frame df retains the changes. Now let's add another row. Again, we want our changes to stick, so we're going to use the assignment operator. We'll use the rbind function and make sure that the dimensionality of our new row agrees with our data frame. And now we can see that the changes stuck with our data frame. Now suppose that we want to convert our new data frame back into a matrix. This can be accomplished using the as.matrix function, just like we used the as.dataframe function to convert it to a data frame in the first place. To be sure that the conversion worked, we'll call the class function. This will output the data type of each object. The next object we'll study is the list. Lists are useful for binding objects together of disparate types. To create a list, we simply call the list function. Also, we can add names to the constituents by creating variables within the list function, as we did with data frames. We can reference members of the list in one of two ways, both of which involve square brackets. First, we can use single square brackets and simply specify the name of the object we want to reference. If we know the index of our desired object, we can specify that within double square brackets. Notice that unlike many programming languages, R indexes from 1 instead of from 0. Let's create another list and append it to the first one using this C function. It's tempting to think that we might be able to accomplish the same thing using a nested application of the list function, but this just creates a nested list. The next type of object that we'll cover is the histogram. The histogram is one of my personal favorite utilities of the R language. To start, let's create 100 random, normally distributed values using the rnorm function. To create a histogram, we simply call the hist function. By default, R will try to plot our histogram. If we don't want this feature, simply set the plot functionality to false. To see its full contents, type H or the name of the variable into which we stored the histogram object. For more compact output, use the str function. To determine the number of bins in the histogram, we can use the length function and reference the counts portion of the histogram using the $ operator. Now we'll talk about creating custom bin sizes for the R histograms. First, let's consider the maximum and minimum of the values that we have using the max and min functions respectively. If we want to round down a value, we call the floor function. If we want to round it up, we call the ceiling function. Using these four functions, we can create custom bin sizes for our histogram. Let's start by creating variables corresponding to the integer upper and lower bounds of the values we wish to study. For the lower bound, we'll combine the floor function with the min function. For the upper bound, we'll combine the ceiling function with the max function. Let's specify the boundaries of our new bins by calling the sequence function, or seq. The seq function requires a lower bound, or in our case min x, an upper bound, or in our case max x, and a step size. Let's just choose 0.2. To tell the histogram function to use this new sequence that we created, we simply specify it using the breaks keyword. Now, by using the length keyword, we can see that the histogram size changed appropriately. Let's figure out which bin occurred most frequently. We can do that by calling the max function on the counts. Again, we need the object, or h in this case, followed by the $sign, next followed by the word counts. And there we have the number of observations that occur most frequently. To determine which bin this value corresponds to, we use the which function. Simply specify as a Boolean statement counts equals max of counts. Notice that the Boolean statement has two equal signs as opposed to one. Single equal signs are used for assignment only. This returns the index into counts, which made the Boolean statement true. Notice that the number is 14. To find out which bin that corresponded to, let's index into the 14th element of the breaks. That's negative 0.4. Let's repeat this experiment, but this time let's use 1,000 values instead of 100. Again, we're going to call the rnorm function, but this time specifying 1,000 values instead of 100. Now let's try to construct a histogram out of these values. Watch what happens if we try to use the same breaks that we had before. We error. Why did this happen? Well, this time we have a new distribution which is most likely outside of the bounds of our previous one. We can fix this by creating new breaks just like we did last time. Again, we'll call the sequence function and use the floor of the minimum value of our new distribution as the beginning. For the second value, we'll use the ceiling of the maximum value of our distribution. For consistency with our previous example, let's use a step size of 0.2. Now let's apply the histogram function once more. Now let's use the methodology of last time to figure out which bin occurred most. Again, we're going to call the which function, and the condition inside is going to be the maximum number of observations. This will give us the desired index. Then we can go back into the breaks and see which bin corresponded to this. This time we get negative 0.2. This is a little better than we did before and closer to what we'd expect from a normal distribution, which is centered at 0. Notice that thus far, all of our examples have been completely numeric. This brings us to our next section, plotting. Let's go ahead and explore the concept of plotting using the histograms that we've studied thus far. We'd like to output a file containing the result of our plot. R has different functionality to output different file types such as PNG, JPEG, etc., but for now we'll just use PDFs. We specify that we want to obtain a PDF file by using the PDF function. Just simply specify PDF and the name that we'd like to have. Then we specify what we'd like to plot, followed by dev.auth. This tells R that it's okay to go ahead and output the file, but we see that we didn't actually output anything onto our desktop. Why is this? This is because R does not understand that the working directory that we'd like is our desktop. So let's go ahead and find that by opening up a new Cygwin terminal and figuring out where we are in our directory. This requires a little bit of insight into what Cygwin actually is. Cygwin is basically a Linux emulator for Windows, which requires it to kind of build its own directory structure. So we can navigate through this directory structure onto our desktop by going to Cygdrive, C, user, my username is nqtuser, then desktop. Using this string, we can specify the desktop as our working directory. So go ahead and highlight it, select copy, go back to R, and set this as the path of working directory using the setwd function. Don't forget that this is a string, so it needs to be surrounded by double quotes or single quotes. Now, if we repeat the exercise from before using the PDF function, we should be able to see an icon pop up on the desktop corresponding to the plot that we just created. If we double click on the icon, we'll actually be able to see the image. It looks pretty good, but now let's go ahead and customize it. Let's repeat the same procedure, but this time let's give it a different file name to distinguish it from the one we just created. To create a name for our plot, simply use the main function and then specify a string. To specify a name for the x-axis, we can use the xlabel or xlab function and set that equal to a string. Similarly, we can use the ylabel or ylab function to set a name for the y-axis. This is going to show us a histogram of our 100 normally distributed points. Let's repeat the same procedure on the 1,000 normally distributed points. That way we can compare the two histograms visually. Again, we're going to call the PDF function to let R know that we'd like a PDF output. This time, let's specify the fact that we have 1,000 points in the name of the file. Again, we call the plot function with the appropriate set of arguments. Calling the dev.auth function lets R know that we're done writing to file and that it can go ahead and produce the output. Just as we expected, it's a much finer looking histogram. Let's have some more fun with plots. We can draw a lot more things than just histograms. Let's try a series of points. Let's specify some x values ranging from -10 to 10. We do this by calling the c function and specifying that range. For the y values, I'm simply going to take the square of the x values. R is really good about applying operations vector-wise. That means I don't have to actually go and apply the square operation to each value in x. R will do that for me. Now I have the values I'd like to plot. Let's actually generate the plot, so we'll call the PDF function first as we did before. We will call our plot parabola.pdf. You'll see why in a second. To create the plot, call the plot function, and this time we want to plot y as a function of x, so we use the tilde operator to do that, y tilde x. That's pronounced y varying with x. As the name implies, the result is a parabola. We can also plot this function a second way. That is, by calling the plot function and specifying the x values first, and then the y values. I'll simply call this parabola 2. Let's go ahead and open this, and we see that as expected we get the exact same thing. Let's generate a third plot. This time we'll call it parabola 3, and this time let's add some options to our graph. We'll plot the same points, this time using the tilde convention. Then we'll add some more options to the graph. We'll start by giving it a name using the main function. Again, we simply set that to a string. Now let's label our x and y axis. Clicking on the output PDF file, we see exactly what we expected, which is a nice parabola with labeled axes and a title. Let's talk about some more plotting options. I'm not going to attempt a thorough treatment of all the different plot options you could do in R. That would take way too long. But what I can do is try to help you figure out how to do that yourself. Go back to the terminal and type $plot. As you see, this gives a thorough description of the plot function. This is not just limited to plot. Every function in R has a description like this. If you go down to the bottom, we usually find some useful examples. Let's play with actually how R generates this plot. If you noticed before, in all of our graphs, we had a series of dots. That's because R tries to plot this way by default. But we can change that. Let's plot a continuous line going through all the points. We'll start out just like we did before by calling the PDF function and giving our file a name. Then we'll call the plot function, specify what we'd like to plot, then we can add the options that we'd like. First, we'll specify the title. Then, we'll tell the graph that we want a continuous line by saying type equals L. Dev.off finishes writing the output file. And there you have it, a nice continuous line connecting all points of the parabola. Let's try a different plot style. This time, I'd like to see all the points and the line connecting them. We specify this option by saying type equals B. As we see, the graph contains all the points and the line connecting them. Now let's try another example where we bring in all of these options together. We'll add some new options like adding color to the graph and also output two different graphs to the same file. We start, as usual, by calling the PDF function with the name of the plot we'd like to output. Let's plot our first function. Again, we call the plot function. And just as before, we're going to plot y varying with x. Let's give our graph a title. Let's also color it red. We do so by calling the color or call function. Then we add a dot, and next we specify what we'd like to color, in this case, main. We can add a subtitle to the graph by calling the sub keyword. Let's color the subtitle too. We do so by calling the col function, adding a dot, and then specifying sub. This time let's color it blue. For completeness, let's not forget our axes labels. To create another plot within the same file, we just call the plot function again. This time I want to plot the identity function or just x equals x. I want to see both the points that form it and the line connecting them. Also, I'm not going to give any axes labels. Again, calling dev.auth finishes the process. Let's go ahead and open the output file. This time we see it consists of 2 pages corresponding to each graph. We will conclude this tutorial by talking about how to create our own functions. In this case, we'll be coding up the function f of x equals x squared plus 1. Creating a function in R is very similar to creating variables. We're going to use the assignment operator followed by the function keyword. This is followed by all the parameters that we're going to need enclosed by parentheses. Next, take a new line and add a curly brace. Our function body is going to be within these curly braces, but all we really want to do is just return the value x squared plus 1. So we use the return keyword followed by x squared plus 1 and finish our function definition. Let's plot our function to make sure that we got what we expected. Again, we'll call the PDF function to let R know that we want to output a PDF. Since this is the first function we're creating, let's just call it function 1. If we don't want to specify any other options, we can simply tell R to plot F. It's that easy. Don't forget to call dev.auth to finish writing to the file. This is the graph that the plot function creates with default parameters. Notice that it's only half of the parabola. The good news is we can specify the x values of the function that we'd like to see. Let's create another graph and include this option. Since this is our second graph, let's call this function 2.pdf. Again, we're going to use the plot function. The first argument is going to be what we want to graph, and that's our function f. Using the xlim keyword, we can specify the range of x values that we want in our graph. The xlim keyword expects 2 parameters, the upper and lower bound to our x values. We'll bind them together with the c function. This time, the output gives us that nice symmetric parabola that we expect. R has many different plot options. We've really only scratched the surface. But I'd still like to show you one more, and that's the log scale option. I'll name this function logscale.pdf. We want the same parameters as before with the addition of the log scale option. This is specified by writing log equals y, since we want to apply the log scale to the range of the function. We see that the output is a rather distorted looking parabola. The log scale is really handy for dealing with exponential functions and other functions which produce really big values. Let's conclude by creating one more function. I'll call it g, and this time g is going to have 2 parameters, whereas before we only had one value, and that was x. Again, we use our curly braces to specify the body of the function, which is just going to be cosine x plus sine y. Notice that I'm not using the return keyword here. It's somewhat of a shortcut. Let's feed some values into g to make sure that we get what we expect. There are some amazing ways to graph 2D functions in R. most of which require external packages that we're not going to get into in this tutorial. That's about it for now. Thanks for watching, and don't forget to subscribe for more videos on data mining in R and quantitative finance using NinjaTrader.